Hello everyone. In this video, I would like to take a look at the definition of a function in a couple different ways that we can represent a function. So on the screen here, I do have the definition to remind us. It says, let x and y be two non-empty sets. Non-empty, all that means is that these sets do have something in them. Maybe they're numbers, maybe they're letters. It can be a bunch of different things, but non-empty just means that there's something in these sets. A function then, a function f, so f there, that's just the name, from x to y is a relation that associates with each element of x exactly one element of y. And this piece here, this exactly one, that's the really important piece that makes a function a function. So in other words, we know what equations are. We've worked with them a lot, but a function is just, it's a special type of equation. It has a special requirement on it. So with the name f, one of the common ways that we can represent a function is I could say that the function f, so that's the name of the function, and then I can describe exactly what it's doing. So function f is telling me that I'm going from things that are in set x, and I'm going to end up with things that are in set y. Okay, so that's sort of just the notation way that we can do this. We can also describe this in a couple other ways. For example, I can represent this with a diagram. So let's say this represents our two sets. And we'll do just a specific example here to illustrate. So this is my set x, and this is my set y. Now maybe in x I have a couple numbers, maybe like 1, 2, 3. And let's say we have a function rule. So our function f is going to do something. And it's going to do something on our variable x. And then on the other side of the equal sign, we describe what the rule is. So maybe for this function, we just double it. So my function f, it's going to do something to x. And what it does is it takes that value of x and doubles it. So for 1, when I map this over, so then this action here, this is my function. This is what I'm doing to it. And we end up with 2. And 2, this is going to map over to 4. And then our last one, 3, this maps over to 6. Okay, so that's just one example of how we can represent a function. Now, just in general, let's say I had something in my set x, and then let's just, I don't know, maybe it's a point, and let's call it x, or it could be a, b, doesn't matter. Now, when I apply my function, this will map to another point, or another letter, or another whatever it is in y, and my result, this is what we call the image of x. So after I do something to it, that's my image, and this is going to be called f of x. So that notation, that is just telling me what my image is. So this notation represents what I end up with after I use my function. All right. Now I did say that the really important part here is the exactly one element of y. So let me show you an example of something that is not a function. So we'll do 2 more sets. And then again, let's label these. So let's say this is set x, and this is set y. And let's say in this set, we have a couple different things. I'll just use letters for this. So let's say we have A, and we have B, and then in set Y, we have the letters C, D, and E. Now let's say we have a function that takes us from x to y. And let's say that when we do this, A maps to C. So that when I do my function, this is what I end up with. But then when I do my function for b, maybe B maps to D, and it also maps to E. So in this case, this is not a function. So because one of our elements in X actually has two elements in Y, this is not a function. It is okay that you go the other direction though. So let's say I had two different values in my set X and they went to the same value in Y, that would be okay. It's just as long as each value in X matches up with 1 and exactly 1 Y.